Welcome back to Autonomous Mobile Robots. I am Margareta Chli, and in this segment we're going to look into line extraction from point clouds. The main problems that we're dealing with when extracting lines from a point cloud is essentially we don't know how many lines there are or which points belong to which line. But the problem that we're actually going to focus on in this segment is this line fitting or extraction problem. So given that points belong to a line, how can we estimate the parameters of this line? So the algorithms that we're going to see are split and merge, the ransack, and the how transform. The split and merge originates from computer vision, and it is essentially a recursive procedure of fitting and splitting. So let's see how it works via this simple animation. We initialize the set S to contain all of the points. We fit a line through all the points present in S, and we find the most distant point to the line. If the distance of this point is bigger than a threshold, then we split the set and repeat with the left and the right sets. So here is again, when we're fitting the points to a line, we proceed in the same way until we have no more splits, which from that case onwards, the merge stage takes place, where we look at consecutive line segments that are close enough to each other in order to merge them. So in this case, we haven't seen any merging, but in this example, merging actually needs to happen. So here we're going to see a slightly different version of the split and merge, of the standard split and merge algorithm, which we call iterative endpoint fit. So what we do is that we simply connect the endpoints that appear in the initial set for line fitting. So here we selected the endpoints, fit the line through them, and then at the next stage, what we need to do, we find the point that is furthest away from this, and since the distance of this point to the line is greater than the threshold, we need to split our line into two. Then again, we look for the furthest away points, and here more splits happen. Now, at this stage, we have no more splits because the distance of the furthest away points to any lines do not surpass the threshold. So what we need to do, we check consecutive line segments, and if they are very similar, if they share very similar parameters, then we merge them, which is what happens here. So now we're going to look at a more popular algorithm, namely ransack. So ransack stands for Random Sample Consensus. So this algorithm is generic and robust, and the idea is that it's fitting models to data in the presence of outliers. So it is applicable to any problem where the goal is to identify the inliers that satisfy a predefined model. Now, ransack has a lot of applications in robotics, and here I name just a few. Some important things to remember about this algorithm is that it is iterative and non-deterministic. That is, that results are different between runs, which is also can be considered as a drawback of this approach. So let's see how ransack works. Consider this problem where we have this point cloud and we are looking to fit a line through all of these points. How do we do it? Ransack selects a sample of 2 points at random and then calculates the model parameters that fit the data in the sample. Then ransack proceeds on to calculate the error function for each data point in the whole set. Then it selects the data that supports the current hypothesis and saves this hypothesis. Then sampling is repeated, which is what you see here, until it arrives to the hypothesis with the maximal support within the predefined number of iterations that we wanted to run ransack for. How many iterations does ransack actually need? The problem is that we cannot know in advance if the observed set contains the maximal number of inliers. So ideally, one could check all possible combinations of 2 points in this line extraction example in the dataset of n points. But what would that mean? That would mean that we'd have this number of pairwise combinations, which is obviously computationally infeasible if n is too large. So in this example here, you can see if we have a laser scan of 360 points, we need to check almost 65,000 point combinations. But the question is, do we really need to check all of these possibilities, or can we stop RANSAC after a few iterations? Usually, checking a subset of these combinations is enough if we have a rough estimate of the percentage of inliers in our dataset. And this can be done in a probabilistic way. Now, if W is the number of inliers over the total number of points, then W actually corresponds to the fraction of inliers in the set. That is, it represents the probability of selecting one point from the dataset that is actually an inlier. Now, let's define also small p to be the probability of selecting a minimal set of points free of outliers. Let's assume that in this line fitting example, the 2 points that are necessary to estimate the line are selected independently. What would be the probability that both selected points are inliers? What we need to do is essentially look back at some of the notation that we introduced before. So the probability that we select 2 inlier points essentially corresponds to W squared. And correspondingly, this 1 minus W squared corresponds to the probability that at least one of these 2 points is an outlier. Now, let's define K to be the number of RANSAC iterations that have been executed so far. What would then be the probability that RANSAC never selects 2 points that are both inliers? So using the probabilities that we computed before, we can actually define this to be 1 minus W squared to the power of K. And actually, if we look back to how we defined small p to be, we can come up with this expression here. And therefore, if we solve for k, we can arrive at the expression that the number of RANSAC inliers the number of RANSAC iterations that we need correspond to this fraction of logarithms here. Now, you can see that here essentially we need W and we also need P. So in practice, we only need a rough estimate of W, and some more advanced variants of RANSAC can estimate the fraction of inliers adaptively and set it on every iteration. Now on to the final line extraction algorithm that we're going to see today, the Howe transform. So here points vote for plausible line locations. And the main idea is that we map the image space to the Howe parameter space. The Howe space parameterizes with respect to the line characteristics. And in practice, this is essentially a discretized accumulator array. So this comprises of voting bins. So let's see how this works. A line in the image space corresponds to a point in Howe space. Why is this? This is because in this case, we parameterize our Howe space with respect to M and B, where M and B correspond to how we defined the equation of the line in image space. So what does a point in image space correspond to in Howe space? That would actually look like a line. If you had 2 points in the image space, what would be the line that connects both of these points? Now, in order to do this, we essentially can see that we have in Howe parameter space one line for each point, and their intersection corresponds to exactly the parameters of this line in image space. So using this principle, every point in image space can vote for different line parameters in Howe parameter space, which is, as we said before, a discrete accumulator array. Now, some problems that we have with the parameterization that we have just seen is that we have an unbounded parameter domain, and also vertical lines require infinite m. So in order to solve this, we use polar representation. Now, in polar representation, every point in the image will map to a sinusoid in the rho and theta parameter space, where rho and theta are defined as you see in this diagram here. To conclude this section, let's look at the relative merits, the algorithms that we have studied today. So the split and merge is the fastest. It's deterministic, and it's making use of the sequential ordering of the raw scan points. This is typically the case when obtaining a point cloud with a laser beam. Now, if we were to apply line extraction algorithms on randomly captured points, then only Ransach and Howe transform would be able to segment the lines. Finally, we need to point out that Ransach and Howe transform are a lot more robust outliers than what split and merge is. And with this, we conclude this segment.